Well, good morning, everyone. I'd encourage you to come and grab a seat. If we've not met, my name is Matt King from the University of Tasmania, and I'll be chairing us today for what I think will be a really exciting session as we explore crisis in the cryosphere. Now, before we have our first speaker today, we're actually going to have a special presentation, and I'm going to welcome to the stage Shin Sugiyama, the President of the International Glaciological Society, to make that presentation. Thanks, Shin.
Good morning, everyone. My name is Shin Sugiyama from Hokkaido University in Japan, and I'm taking the role of IGS, International Glaciological Society, President since February last year. And today, this morning, I'm very glad to share with you this time to present the IGS Early Career Scientist Award to Lauren Vargo. I have a paper to read. Are you okay with me? Okay. So this award is given in recognition of significant scientific and community commitment to glaciology by an early career scientist. So I want to read the citation of this award to Lauren. Dr. Lauren Vargo from Victoria University of Wellington, Te Herenga Waka, is an exceptional early career scientist who has demonstrated an extraordinary commitment to glaciology, combining innovative research with a passion for science, communication, and community service. Dr. Vargo's most impactful research contribution to date has been the development of an attribution framework linking extreme individual glacier melt events to human-driven climate change. She demonstrated that extreme melting on glaciers, the years when the highest ice loss occurs, were far more likely in a human-influenced climate. This research was a key citation in demonstrating the human fingerprint on glacial retreat in the recent sixth assessment report of the Intergovernmental Panel on Climate Change. Dr. Vargo has also been instrumental in maintaining and updating long-term records of mass balance in Aotearoa, New Zealand's South Alps. Using historical photographic sources and structure from motion photogrammetry, Dr. Vargo created precise models of glacier change. This innovation has transformed the long-standing End of Summer Snowline project, which uses snowlines as a proxy for mass balance, to include direct observations of geodetic mass balance changes, enhancing the program's value in the 21st century. She has also been a key researcher in the now 20-year-long record of mass balance from Blue Star Glacier. Dr. Vargo's contributions extend far beyond her research. She co-founded the Girls on Ice program in Aotearoa, New Zealand, leading the first expedition in January 2024. She also serves as Aotearoa, New Zealand's national delegate to the World Climate Research Program, WCRP, and she is a member of the Scientific Steering Group for Climate and Cryosphere, CliC, and holds leadership roles in the International Association for Cryospheric Science, IACS. She has demonstrated enormous aptitude for communicating science to more general audiences. She regularly visits primary and secondary schools in Aotearoa, New Zealand, bringing glaciers and climate science to life for students, and communicates her work through public engagement via popular science writing, direct engagement with decision makers, and public talks and media interviews. Dr. Vargo's research has made an invaluable contribution to understanding the effects of human-driving climate change on mountain glaciers, and her ability to present complex glaciological phenomena in a clear and assured manner has earned her respect both in the scientific community and in public discourse. On behalf of the Award Committee of the International Glaciological Society, congratulations, Lauren, and waka miho.
Thanks so much.
This is for me.
All right, a massive thank you to the IGS and Shin for those kind words. And a massive thank you to the people who nominated me for that award. Most of them are conveniently here today. Brian Anderson, Heather Purdy, Andrew McIntosh. I didn't know they were nominating me, so I hope that's everyone, maybe Regina too. And conveniently, they're the same people together with Nicholas Cullen and Drew Laurie, who I would have thanked ahead of this talk anyway, for their work in starting and continuing glacier monitoring here in New Zealand. Being part of those projects has been something I've really enjoyed the past 10 years, but that data has been really key in the work that I've done and what I'll talk about. So here we're looking at a map of the Aoraki Mount Cook region. It's in the central South Island where the majority of the glaciers in New Zealand are. We're looking at elevation change from the Huguenot et al. Work, and it's flipping from 2000 to 2019. We can see the glaciers popping out in red. So the darkest reds are years of the largest elevation lowering, so glacier thinning. We can see that towards the start of the record, the reds are a bit paler, sort of pink, but towards the end, they're quite dark, so showing that New Zealand glaciers are losing mass, but that rate of mass loss is really accelerating. And that trend isn't unique to New Zealand. Glaciers around the world are losing mass. So this is work from the recent Glanby team, collating measurements of glacier mass balance. And each of those pie charts are a region with glaciers around the world. Each of those little bars underneath the pie chart is the mass balance for glaciers in that region for that year, starting in 2000 and going to 2023. We can see that most of the bars are red, and if we look at the global average, globally, glaciers around New Zealand have been losing, glaciers globally have been losing mass since 2000. And we see those reds getting darker, so that rate of mass loss accelerating over the last 25 years or so. And we know that glaciers will likely continue to get smaller in the future. So this is one of many projection papers that have been being done in the last few years, looking at global glacier volume change and how it might change by 2100. Globally, if we're able to mitigate greenhouse gas emissions, we might lose about a quarter of glacier volume change. That's that blue line there. Whereas if we continue rates of warming, we might lose about half. This is from that same study for New Zealand, and the picture's a bit different, quite more dramatic. So even if we're able to mitigate greenhouse gas emissions, we'll still probably lose about half of our glaciers here in New Zealand by 2100. And current rates of greenhouse gas emissions and warming will likely result in losing almost all of that ice mass. So because I don't think everyone in this room thinks about mountain glaciers day to day, I thought I'd chat quickly about why we care about these. A big one is sea level rise. So sea level has risen about 10 centimeters over the past few decades. That's relevant around the world, but also here in New Zealand with so much of the community and infrastructure being around coasts. Glacier melt has been a big part of that. Glaciers are also important for water resources. There was a wonderful talk yesterday about the importance of glaciers for hydropower in Norway. Communities like South America and the Himalayas, glaciers are a really significant source of fresh water. Here in New Zealand, it's wet enough that we're not so dependent on them for water, but they are still important, especially in drought years, which we've seen more commonly. As glaciers have been changing, we see hazards associated with that. There have been some really dramatic glacier outburst floods in Asia that have caused loss of life, major damage to infrastructure. Again, here in New Zealand, we haven't seen such dramatic impacts, but this is a photo from downstream of the Franz Josef Glacier on the left. Heather Purdy, who's here, I know has done a lot of work and talked a lot about her experience as glaciers have retreated and thinned, the resulting impacts on access to the mountains, becoming harder and less safe. And then tourism. I think in New Zealand and around the world, glaciers are a part of this. There are millions of visitors to glaciers in New Zealand every year. And here in New Zealand, glaciers are a taonga, a sort of treasure. The indigenous people, Maori, were observing glaciers for a long time. So Franz Josef Glacier also has the name Ka Roemata o Hine Hukatere, or the Tears of Hine Hukatere. So just showing the significance of these culturally. So for all those reasons that we care about glaciers, it's important to know how they're changing. Again, this is that Glanby paper. So there have been some major global advances in how we measure glacier change. A few other papers are highlighted over on the left. But one thing that stands out in lots of these global studies is that New Zealand glacier measurements often have these really high uncertainties, usually the highest of any of these 20 or so regions where there are glaciers. We can see that here. We're looking at, there we go. We're looking at glacier mass balance for all of these different regions. The New Zealand glacier mass balance is over here, and we've got this massive error bar associated with the measurements from this study. And this isn't unique. Most of the global studies that I've noted have the same findings. There are about 3,000 glaciers in New Zealand, but they're very small. So I think part of these big uncertainties come from that. They're hard to measure, but also because we don't actually have heaps of measurements from them. So now I'll talk a little bit about the ways that we do measure glaciers here in New Zealand. One is the end of summer snowline survey. This is something that I've been really happy to have been involved with since I've been here, but it's been going since the 70s. It involves taking photos of glaciers annually to get a look at the end of summer snowline, so how much snow is covering the glacier. Here we're looking at Brewster Glacier in 1992. We can see that the whole glacier is covered in snow, so a really low snowline elevation this year. Then in 1999, it's a bit harder to see, but that's mostly bare ice on the glacier surface. So a really high elevation snowline, signaling that the glacier would have melted more that year. Doing this for about 50 glaciers around the Southern Alps generates this end of summer snowline anomaly plot that we see right here. Years with high snowline elevations indicate years that the glaciers likely lost mass, and low snowline elevations are years that the glaciers would have likely gained mass. So a couple things to note. One is that we see kind of lower snowline elevations towards the start of the record. But more recently, and this plot is only updated to 2020, we start to see these much higher snowline elevations. Another important thing to note is that these are kind of only indicative of glacier change. There's no sort of direct link between what the snowline is doing and how much New Zealand glaciers are changing mass, which is what those other global studies are looking to do. So there are some ways that we do measure that here in New Zealand. So out of our 3,000 or so glaciers, there are 2 that we visit every year. And I use we in the large sense. So one is Rolleston Glacier. I've never been involved in that. That's led by Heather and her team at the University of Canterbury. That record is shown here in this red line. And then Brewster Glacier, which Brian, Andrew, Nicholas started, and I've been happy to be involved with since then. In the gray line, those are plotted here. They're cumulative mass change since 2010, together with the WGMS reference glaciers. We can see a pretty continuous mass loss over the last almost 15 years or so. The reason we only have these 2 measurements, these 2 glaciers, is because it takes a lot of time and effort and money. So there is another way that we've started measuring how glaciers are changing, and that's using structure for motion photogrammetry. So taking hundreds of photos of a glacier. We do this from a small airplane. Other people in other regions will do it from using drones. In that airplane, we also have GPS and really precise timing so that we can know the location of the images really accurately. This has been going on for 10 years now, every March or so. And from the structure for motion models, we can get pretty ortho photos, like we see here, again of Brewster, flipping between March 2016 and March 2019. So these look nice. You can get an idea of how glacier area is changing, but especially exciting from the structure for motion work are the elevation models that come from it. So on the right are the elevation models difference for that same time period as we're seeing on the left. We can see pretty dramatic thinning of the glacier just over those 3 years. And we can use this data over the 10 years to get longer-term measurements of the geodetic mass balance, so taken from these images, differencing the DEMs. On the left, we're looking at the record for Brewster Glacier, on the right for Rolleston. And the 2 different lines are just, one is the annual DEM differencing, and one is the start to the end of the record. And what's quite interesting, beyond just seeing this record of mass loss, is to then compare these measurements with the other measurements that we have. So in blue are the field measurements, the glaciological measurements that I just talked about. And in purple are the geodetic satellite measurements. So those measurements from that study that I showed in one of those first slides where we were seeing that map with the thinning rates. We can see that, especially for Brewster, the field measurements and the other studies seem to really be underestimating the mass loss that's occurring by almost 50%, sort of by the end of the time that we've got here. At Rolleston, not quite so much underestimating, which is fabulous. But then really interesting to see both the difference in that global study in purple right here, and again, the massive error bars, which if you want to know how glaciers changing, having that much uncertainty isn't really useful. So before I move on, I just wanted to use this slide to plug Felix, a master's student working with me, has a poster later today where he's done some really cool work to process this structure for motion data differently in a way that reduces the errors even further to what I've done here to ultimately use them for kind of different things. But if we're looking at getting back to these records, brings the question, how do we better measure glacier change in New Zealand? This is something that I think I and colleagues have only just started thinking about, or maybe have thought about for a while, but haven't really thought about how to what to do. It's probably some combination of using all of these measurements together with some sort of New Zealand-wide modeling. I also wanted to mention some of the attribution work that I've done, which Shin also nicely introduced, showing formally that mass loss that we can see that I've shown previously from the measurements, that we know that that is due to anthropogenic climate change. So using a combination of event attribution methods together with glacier modeling, I simulate glacier change with and without anthropogenic climate change. So on this plot, we're looking at probability distributions of Brewster Glacier mass balance for a given year. In the black is that probability distribution without anthropogenic climate change. So what mass balance in any one year might have been without increasing temperatures that we see today. In red is the same mass balance probability, but with climate change, sort of in today's world. And then in blue is the measured mass balance, the glaciological mass balance at Brewster Glacier in 2018. At the time that I did this work, that was the most negative mass balance year on record. And the results of this attribution work show that the mass loss that we saw at Brewster Glacier was at least 23 times more likely to have occurred due to anthropogenic climate change. So starting to wrap up, this is a figure of work that I wasn't involved in at all by Brian Anderson. And I think it kind of, I hope that it shows a bit of a hopeful message in that, again, we're looking at the Aoraki Mount Cook region with the glaciers there. But knowing that glaciers in New Zealand and around the world are melting, but what they do in the future is up to us. So we have this scenario where they could look similar to how they look today, still recognizable, both in New Zealand and around the world, if we can mitigate greenhouse gas emissions and warming. Whereas with 5 degrees of warming or so, we lose essentially all of the glacier mass in New Zealand and just have ice sort of at the highest peaks. And then I wanted to finish on something that does make me feel hopeful. So a program that I've been running for the past few years here is Girls on Ice New Zealand. We take teen girls to Mount Ruapehu to do art and science and outdoor exploration. And seeing their enthusiasm and what they get out of this is something that is one of the times that I kind of feel most hopeful for the future. And this is a project that if anyone's interested in chatting more or getting involved in, I'd love to chat more with, or my colleague Julia Martin, who is here teaching some students about snow. You can also find her and chat with her about it. And I will end on that note.
Our next speaker is Professor Chris Stokes. Chris is a glaciologist in the Department of Geography at Durham University in the UK. His research is focused on glaciers and their interaction with the ocean climate system across a broad range of spatial and temporal scales, but with a particular focus on their response to climate warming. This includes monitoring small mountain glaciers over the last few decades to large-scale reconstructions of ice sheets over tens of thousands of years. Most recently, Chris's work has examined the sensitivity of the ice sheets to specific temperature targets, such as those in the Paris Climate Agreement. This has led to opportunities to present his work to policymakers at the Conference of Parties, the COPs, and other meetings under the auspices of the United Nations Framework Convention on Climate Change, as well as extensive media engagement and outreach activities. We'll welcome Chris Stokes to the stage. Thanks, Chris.
Thank you very much, and I'd really like to thank the organisers for inviting me to this conference. And the invitation was to kind of pick up some of the themes from this paper that was published last year. And I think it's worth saying kind of a little bit about where this paper came from. It was actually in a technical workshop on the Cryosphere that was designed to inform policymakers at the Bonn Climate Conference, which is the kind of intersessional conference that takes place in between the COPs. And there were various Cryosphere scientists presenting the work, and the emphasis was really on trying to take 2 degrees off the table in terms of the negotiations. The Paris Agreement aims to limit warming to 2 degrees, but ideally 1.5. And there was a very strong sense in the room, this was just a couple of years ago, that actually if you were renegotiating the Paris Agreement, you would not be saying that 2 degrees is okay for the cryosphere. So the message was getting through that 1.5, and I know there's people in the room who will have contributed to special reports suggesting that, 1.5 really has to be the absolute limit. And we know that that's almost certainly gone, and we're now looking at overshoot scenarios. But there was also a sense that actually if we did make 1.5, all our problems would go away, right? That this would solve sea level rise, it would solve other issues. And actually, there was a kind of misunderstanding in the room amongst some of these climate negotiators and policymakers that 1.5 would actually be fine, we'd be okay with 1.5. And so that got me thinking, and I spoke to a few other scientists, some of whom are co-authors on the paper, about actually, well, what happens to the ice sheets at 1.5? What's happened to them in the last few decades? What's happened to them in the past when temperature was at 1.5? And it motivated this paper, which I'll be talking about today. So what I'll just cover briefly is just a little bit of the context in terms of where we are with regard to global mean temperatures and climate targets. And then we looked at 3 main lines of evidence. We looked at kind of current observations of mass loss. So what are the ice sheets doing now at kind of 1.2, 1.3 degrees of warming? We also looked at sea level during past warm periods and updated some assessments that Andrea Dutton had done previously in a paper in Science. And then we also looked at kind of future projections of change and tipping points and how those have kind of changed over the years as well. And then I'll finish with some conclusions. So this is where we are at the moment, and I'm aware that others have put this very slide up at this conference already. Current warming is somewhere between 1.2, 1.3, depending on what you look at, and that is generally seen as the 20-year average. So there's a little bit of a misunderstanding that we have a very warm year, like 2024, which on average was over 1.5. It doesn't technically mean that we've breached the 1.5 limit, because that's a 20-year average that the IPCC uses. But we're at about that level of warming. And if you look at kind of current policies in action, the blue swathe there, you can see that we're heading for about 2.5 to 2.9 degrees. And you can see that we are way off track with the 1.5 compatible scenario in terms of our carbon emissions. And it was interesting that at the last COP in Belém in Brazil, it's the first time I'd seen a really tacit acknowledgement from some of the leaders and the policymakers there that actually we have now lost 1.5 in the sense that we're now looking at overshoot scenarios. I think the scientific community has known that for quite some time, but everybody's been trying to keep this focus on 1.5. I still think that has to be the focus. I think most countries are on board that we're now looking at a kind of overshoot, but we need to come back down to 1.5. Some will use it as an excuse to say, well, actually, now we can just reset to 2 degrees. But clearly there is a huge emissions gap here, and this is the kind of context within which we're working. We're only at about 1.3 degrees of warming. And even under that current warming, just 1.3 degrees above pre-industrial, we can see that sea level rise is accelerating. This is a plot from a paper that came out a couple of years ago now, and there are pros and cons of the approach that they use, but they plot a trend line through recent data, and they argue that sea level rise has doubled, and they provide some extrapolation of that sea level rise. And if you take that extrapolation towards the end of this century, then sea level rise, if it continues, will be about 1 centimetre per year. So somebody born at the end of this century will be looking at potentially 1 metre of sea level rise within their lifetime, which to me I find incredibly scary. So what have the ice sheets been doing over this last few decades? Well, this plot here is just showing you the 3 ice sheets. Greenland is the kind of turquoise plot. The data here are taken from the latest INBI assessment, the ice sheet mass balance into comparison exercise. And then we added on and spliced it with some recent GRACE data for the last few years, which is why you get slightly more jumpy data set, because that's monthly data. You can see that Greenland has been consistently in a negative mass balance over the last few decades. You can see that West Antarctica has also been consistently in a negative mass balance. East Antarctica is the black line, and that's kind of hovered about zero, but East Antarctica is very vulnerable to kind of weather conditions, if you like. And there's been some really heavy snowfall, particularly in the last few years, that have really helped mitigate some of the sea level rise there. But the bottom line here is that these ice sheets have now added about 25 millimeters to global mean sea level, and I think it's significant that, on average, they're emptying about 350 billion tons of ice into the ocean each year. And whilst small mountain glaciers, such as the ones Lauren talked about previously, dominated the cryosphere's contribution during the last century, I think it's significant now that the ice sheet contribution, the contribution from Greenland and Antarctica, is now larger than for mountain glaciers and ice caps. And I think that's something that we should be concerned about. Now, people are interested in whether there's a kind of statistically significant acceleration in mass loss. This is a long-term record of Greenland ice sheet mass balance going back to the kind of 1850s. And you can see there where the zero mark is. Again, most of this record, it's been negative, but there have been periods where it's lost a bit more mass. There's been periods when it's gained a bit more mass. And you can see here that there's been a kind of quite dramatic fall-off in the last 2 decades. I'm also aware that there's a great paper being presented later at this conference where I think they've got 6 centuries of Greenland ice sheet mass balance. And obviously, the longer the records we have, the more easy it is to determine whether we're seeing something that is beyond the natural variability. I would say that for Greenland, most papers would argue that there is a statistically significant acceleration in mass loss. West Antarctica, much less so, and East Antarctica is largely in balance at the moment. And we need those longer records, but it's very difficult to do, to get proxy records of mass balance, for example, in Antarctica. So I've mentioned that Greenland and West Antarctic ice sheet are dominating the signal of mass loss. But I think there are emerging signs of dynamic change in East Antarctica as well. Those of you who know me will know that I'm very interested in what's happening in East Antarctica, which has often been overlooked, I think, in the past. So if you were just to pull out some decadal scale measurements of grounding line migration, obviously we have some very high rates in the Amundsen Sea embayment, Pine Island, almost 1,000 meters a year grounding line retreat. And again, these are decadal timescales, so that was from 1992 to 2011. These are just some of the highest figures that you can find in the literature. But you can see over in East Antarctica, there are also some signs of mass loss, particularly in Wilkes Land and potentially down here as well. And if you go and look at the literature, there are also some quite alarming rates of grounding line retreat in East Antarctica. So Denman, Vanderford, Totten has been studied probably the most of all East Antarctic outlet glaciers, but actually its grounding line retreat is not as high as some others. Moscow University is higher. And I just want to highlight some work of a master's student at Durham that I've been working with, who's been working on these glaciers down here. And actually, if correct, and these grounding line measurements do come with quite large uncertainties, then actually, you know, some of these grounding line retreat rates in East Antarctica are on a par with those seen in the Amundsen Sea. And they're also in areas where we're seeing the ice sheet lose mass. And of course, there's CliC as well. So I think this is very worrying. All this is happening at just 1.3 degrees of warming. And one of the other points that I tried to make is this is just a bar chart of publications on West Antarctica versus East Antarctica in red. And you can see that although the ice sheet is huge, it's still relatively understudied compared to the West Antarctic ice sheet. And there's good reasons for that, of course. But I'd like to think that East Antarctica is catching up over the last few years. And I think actually this part of the world, there's world-leading research coming out on the East Antarctic ice sheet, which reminded me that I need to update this bar chart. And hopefully we'll see some further publications on East Antarctica. The other thing we did in this paper was look at sea level during past warm periods. And Andrea led on this part of the paper. She'd earlier suggested that we're looking at maybe 5 to 9 meters of sea level rise during the last interglacial. Actually, the uncertainties there have increased because of some complicated GIA effects and improvements in our understanding of the GIA effects. But we can expect several meters of sea level rise. What you're looking at here is the kind of the forcing, both in terms of the global mean temperature, but what the temperatures were in the Arctic and Antarctic during marine isotope stage 5. Then you get the Greenland ice sheet response, the Antarctic ice sheet response, the peak global mean sea level. So there's a lot of information on here. Bear in mind that we're currently at about 424 parts per million and 1.2 to 1.3 degrees of warming. And you can see here that we've got, during the last interglacial, It's cooler than today, much less CO2 than today, and yet sea levels were 2 to 9 meters higher. We can go to stage 11, which is another interglacial, which was quite long, and a candidate for kind of an analog for future climates. Again, it's much less carbon dioxide in the atmosphere. Temperatures similar-ish to today, or where we're heading by the end in the next few decades, and we have sea level that's 6 to 13 meters present. And then during the mid-Pliocene, when it was a bit warmer, CO2 levels were a bit higher than present, and we get 10 to 20 meters above present. So it's very clear from the paleo record that if we warm the planet to these degrees, you do get big ice sheet melt from Antarctica. Now, this is not actually new. You know, this was in the AR6, but I think maybe the understanding is that actually this is locked in, this is committed at these warming levels, but it will take a long time, and therefore we have time to adapt. I think some of the observations of the ice sheet suggest that things are happening perhaps much quicker than we previously thought, but I'm aware that's open to debate. And one of the other things we did is we looked at some computer simulations, and they also seem to show that 1.5 will not slow or stop sea level rise from ice sheets. I think this plot here is from some of Rob DeConto's work. This is at 1.5 forcing. It includes a carving parameterization that leads to relatively or very high rates of mass loss, albeit ones which the IPCC were unable to rule out. But you can clearly say that even at 1.5, then we could be looking at 1.5 meters of sea level rise just from Antarctica. And what Greenland's doing as well is not obviously on this plot at all. And you can see that you could even just force the ice sheet model with a kind of current climate. And most of the modeling experiments that we looked at seem to show that sea level rise does not stop, it does not slow down at 1.5. But there is different models use different parameterizations, there's different feedbacks, and I think it would be fair to say that not all would show the same effect. But I think again the paleo record is informative. We know, for example, from Meltwater Pulse 1A that things happen to ice sheets that potentially led to sea level rise of 3.5 meters per century. There are processes there that we need to be aware of in terms of how quickly ice sheets can lose mass. And I would say that if you look at the recent literature, there is a growing body of evidence suggesting that even under this current warming, present-day climate might be sufficient to tip the ice sheets into unstable retreat. These were a couple of papers actually from over 10 years ago, but there's been a whole series of papers recently looking at unavoidable future increase, tipping points, current rates of mass loss, precursor for collapse, stability of grounding lines, current forcing being capable of tipping them, and thresholds being crossed, etc. So there's a whole bunch of papers now coming out, all suggesting that actually current climate forcing may be sufficient just to start these marine ice sheet instabilities, for example. So just the other thing that I find quite interesting is that our understanding of tipping points has changed over the years. So I went back to some of the old literature, and this is just a plot of the Earth's global temperature. And if you go back to the literature, there are papers written just a few decades ago saying it would take 17 degrees of warming to destabilize the East Antarctic ice sheet. And now we're thinking it's much closer to 2. So the red arrow is kind of pointing to kind of where 2 degrees would be on the plot. If we go to the Greenland ice sheet, again, it's ever so slowly kind of being revised downwards in terms of its tipping point. So from 3.1 to 1.8 to 1.5. And if you adopt the kind of precautionary principle and say, well, what's the kind of minimum possibility, then actually it turns out it could be as low as 0.8, which we've clearly already crossed. And it's similar for West Antarctica, which is thought to be around 1.5, could be as low as 1, but the recent Global Tipping Points report was a very impressive document of all of the available evidence, actually suggesting that a precautionary limit of 0.5 would be appropriate. So again, this spells bad news if it's already too late. And of course, as has been pointed out, if we have crossed these tipping points, we probably won't know for several decades. And that, again, is something I think that we need to be aware of. So to conclude, ice sheet contributions to sea level rise have quadrupled since the 1990s, and they are now the dominant contribution to sea level rise from the cryosphere. Sea level rise is accelerating to rates that will be very challenging to adapt to within the lifetime of our young people, potentially a centimetre per year by the end of century. And so I think it's really clear that policymakers should be preparing for several metres of sea level rise over the coming centuries. But as has been pointed out several times by people at this conference already, every fraction of a degree really matters. And actually decisions taken now will determine how fast and how high that sea level will go. And so it begs the question then, well, if 1.5 is too high, what is a safe limit for ice sheets? And I think this is something that the community could do a little bit more work on, actually. I know it's not an easy question to answer, but having argued, I hope, that 1.5 is too high, the obvious next question is, well, what is a safe limit? And in the paper, we argue that it should be much closer to 1, possibly even lower. And I think, you might think, well, that's pie in the sky, that can't be done. But there are some people working on these kind of emissions trajectories and arguing that actually it is still feasible within the current socio-economic systems. It's incredibly challenging. It requires countries that are currently not on board to be on board, which you might argue is looking rather pessimistic at the moment. But this really nice bit of analysis I'd point you to about kind of rescuing 1.5, reliant on kind of scaling up of renewables. Yes, technology in carbon dioxide removal needs to be there and needs to be scaled up. But they think this is still a possible pathway, and they've presented this to policymakers as a kind of way out, last chance saloon, however implausible or challenging it might be. So I think I'll finish there, and maybe we can pick up some of these themes in the discussion later. Thank you.
Well, thank you, Chris. Now, Chris has given you some provocation there, so I'd expect questions to be pouring into the app, ready for our panel session in just a few minutes' time. But before that, we're going to welcome Professor Petra Heil to the stage. Petra has encouraged me, after the very long introduction for Chris, to provide a short bio. So Petra is now the Director of Science at the British Antarctic Survey. She's a trained polar physicist and a systems scientist. Before that, she was a good friend and colleague at the Australian Antarctic Division and often at the University of Tasmania. And so I'd like to welcome you to tell us about what you're going to tell us about, Petra. Thank you.
Yeah, thanks, Matt. First, I want to thank Matt to wake me up. I had a good sleep in this morning. After 5 days of jet lag, so hope the presentation doesn't suffer too much, but I must admit I fell asleep while I was kind of trying to touch it up. So Antarctic sea ice in transition, looking at it, and the aim was to really pull things together, as we have done recently under a paper, to really also give an outlook of the impacts on the planet as it changes. However, first I wanted to step back and look at the global sea ice. So you're very well familiar with the polar views in the north, the Arctic sea ice, enclosed by land masses. On the top left, you see it's summer minimum, typically reached in September. Here, the last plot second last plot for September 24. And then it's more seasonal winter maximum during March. And you can see the red lines, which are the 30-year climatology from 1980 to 81 to 2010. And you see significant areas of sea ice loss, especially in the summer. It has nearly pulled away from everywhere in the eastern Arctic, in the western Arctic. And most of the sea ice in summer in the Arctic is just attached to those islands here in the northern tips of Greenland. Similar, we have lost a lot of the sea ice here in the Eurasian area of the North Atlantic extension, but also here in the Bering Strait area. The two bottom pictures show you the summer sea ice in Antarctica in the winter on the right, and you see a very detrimental change here to the summer sea ice, which in contrast to the north, we have the land mass sitting over the pole and then a surrounding circumpolar ocean. So the latitudinal change, geographical setting is driving a lot of this. However, we also see the sea ice in Antarctica having really lost around the edges, all around, especially there also where we have those large chiral basins extending and pushing the ice far north towards the equator. If we integrate the sea ice extent as the time series from the satellite record, which started in late 1970s as a global sea ice one, we see that there's a lot of variability. So the darker colors are the earlier years, and then we transition to the last years, and the 2025 is partially shown in red here. And so what you can see is there's this bifurcation between the Arctic dominance with the Arctic winter around February, March, and then we have the shallower signals actually during the Antarctic winter, which speaks to a lot of more inter-annual variability for the Antarctic winter season. But you also can see that overall, the year-to-year differences increase as you go from the darker colors to the lighter colors. And this especially holds up as well during the Antarctic winters, as you can see here, where we have some of the yellows taking these really dips as influenced by the Antarctic demise in the recent years. So separating them out just as a time series, in blue, the curves for the summer. So you have the the winter panel here at sea ice maximum, the summer here. The Arctic sea ice minimum showing a decent amount of inter-annual variability, but overall reasonably flat over this satellite record, but then we have this crash in the last 10 years. We have this Antarctic September record, which coincides at the same time, and we see also, if at all, a slight increase up to this 2014 maximum, over 20 million square kilometers, and then this crash. So if you compare the slopes of those two lines, they're pretty much going hand in hand. However, we also have the Antarctic sea ice minimum, the Antarctic sea ice minimum, and it shows an earlier change in the slope, in the response, and that's in the mid-2010s, where we had some really unusual sea ice pattern in 2007-8 and after. So what happened in the meantime globally? We just heard from Chris about the changes, especially in the ice sheets, and Lauren gave us a global overview over the glaciers. But I guess all the systems we are discussing are sitting underneath an atmosphere, and that atmosphere obviously is giving broad evidence of the anthropogenic changes that we are injecting into it. So the last 150 years of the record, from here the Berkeley data set, and it really shows there is always a range of inter-annual variability, as we very much appreciate. But we have this kind of, well, I don't want to say runaway slope, but we have this really strong upward tilt in the last few years. And as we can see, there's always, in the last 10 or so years, we reach a lot of those very warm temperatures. So 2025 was the third largest year on the record. And we obviously see the changes across our spheres. If we focus now just on the Arctic, the northern polar region, this is the time from 1950 to 2025, and the seasonal from up on top is January to December. We see this warming, but what is very clear in both hemispheres is especially during winter time, so January, February, but also then in autumn and into winter, at the bottom of these graphs, we see those strong warming signals. I appreciate that we earlier in the week heard that the polar amplification is actually reducing. I think there was a slide yesterday or possibly even on Sunday. So that's really interesting for us to understand and to monitor how the sea ice or the glacial cryosphere really will respond to the reduction, and what are the feedback signals, because as we have lost a lot of the cryosphere in the recent decades, that would obviously have contributed to a reduction of further loss and further increase in the temperature in the polar regions. So trying to use the AR6 as a statement to look forward. So in 2021, we were given the summaries that for the Arctic sea ice, it's virtually certain human influence has caused the decline. And there are projections, so numerical simulations, that expect us to see ice-free summers at 2 to 3 degree warming. The timeline for that is around 2050, 2060. For the Antarctic, however, there was just a note that the decline post-2016 is acknowledged, but there has been the statement that overall there is very, very low confidence in the attribution of any Antarctic sea ice changes. So this was before the 22-23 crash of the summer and then since the Antarctic winter sea ice crash. And so it's really interesting to see how the authors of the AR7, who are just commenced their work, will address to discuss the Arctic, the Antarctic, and the global sea ice evolution that has been observed and described by many of us since then. I'm taking the liberty to step back here. So, sea ice, I guess I didn't really introduce it to you because I've been for 2 days just immersed in sea ice day and night. It's very thin. It's covering the polar oceans largely and some of the more marginal oceans, for example, around the coast of Russia, China, Japan. It's forming largely from marine water, so it's frozen seawater. It's not a pure ice. And I know all my Hobart colleagues, when I came in with a sea ice core, they would say, don't bring it in our lab, you will dirty our nice measurements. So it's the dirty ice in the cryosphere, but it has a lot of interactions. This is a plot from the mosaic, from a paper describing the mosaic expedition, which happened in the north, and basically it brings together many, many traits and interactions that the sea ice engages in. So it's thinner, it's about 1, 2, 3, several meters thin, because it deforms, it moves with the ocean currents in the atmosphere, it breaks open and it forms ridges when there are collisions. They have a deep expression, but they also have a surface expression. So these ridges then obviously in the water give cause to drag, turbulence, fluxes. We have also, when there's deformation, the formation of open water areas within the pack. The sea ice drifts differentially in response to a number of forces, wind, internal forces, Coriolis forces, and so on. As soon as there's open water exposed during freezing conditions, we have new ice formation. But there's also continued formation of sea ice at the bottom, as long as there is a negative heat flux from the ocean to the atmosphere. There's a lot of interactions between the sea ice and the overlying snow. As soon as you freeze over the ocean, you obviously provide a curtain on which snow can accumulate and be retransported. And we had some very nice talks yesterday about the effect of snow on the sea ice, especially its thickness distribution, but also its biogeochemical properties. And then if you look further up, obviously having sea ice on top of this relatively dark ocean means we're changing the energy balance at the polar regions. Then as the sea ice ages, it changes its own characteristics. As the sea ice accumulates and transports snow, those radiative properties change again. Also, sea ice is an obstacle for exchanges from the ocean to the atmosphere and vice versa. It provides a feeding ground, a nursery for a range of primary to higher species. And then these engage again in various processes that may lead to aerosol, to gassing out, to aerosol production, and themselves give another feedback loop into the system. So it's a very complex, tightly networked system. And changing just one component in it, for example, the thermodynamics in the first assumption with this global warming, gives a lot of change into the larger sea ice behavior. I couldn't help myself to put also a slide in that a group working on Antarctic sea ice put together. As you can see, the processes also include a lot of cryospheric components. There are the interactions of the sea ice itself, the pack ice. Then we have a lot of focus on the land-fast ice, and we had beautiful presentations about that yesterday. We learned about the platelet ice, which comes from supercooled water, which is coming from the interaction of the water flowing underneath the ice tanks, the glacial ice tanks, and then rising up and settling out under the sea ice, and giving a lot of different properties, but also scope for the sea ice to thicken, but also to harbor different communities and so on. We know there's a strong interaction between the sea ice and the icebergs, especially in the Antarctic, where we have those significantly deep tabular icebergs. Hand in hand with that goes Polynya Formation, which again exposes the exchange between the warm ocean and the much colder atmosphere. And this is a very strong signal around the coast of Antarctica, but also with deep convection further out in the ocean. And then as we move further towards the continent, the sea ice interacts very much with the ice sheet, the glacial ice sheet beyond. So pack ice protects the landfast ice. Landfast ice sits adjacent to the ice shelves or the ice sheets and basically forms a belt holding those up and against onto the continent. We also see the interaction of the sea ice processes with the biogeochemical systems on the water masses that enter into the cavities under the ice shelves and come out. And obviously we heard about what's happening at the other side of the sea ice transects, out in the marginal ice zone, where the sea ice concentration may be less, but also where the sea ice characteristics are very much different than further into the pack. We have been listening to a number of talks that describe the interactions of waves into the sea ice pack, how to detect them, but also we heard yesterday how they feedback and provide changes to the Antarctic sea ice especially, and how this is one of the big signals we have to work with in the coming years, as more and more of the Antarctic sea ice, but also in the Arctic, becomes marginal sea ice zone. And there's a lot of feedback mechanisms that, depending on the seasonality, either work to rapidly reduce the sea ice, to melt it, and to reduce its horizontal extent, but also during winter time, work to actually strengthen the sea ice. So now focusing on Antarctic sea ice change. Obviously, a lot of it is concerned about what are the drivers. I already dropped a lot of names, ocean, atmosphere, so on. You have seen the curve, I assume, quite a bit. We reference back to the beginning of the global satellite record, 1779. This is the sea ice area anomaly. And we have initially, a lot of inter-areal variability as we expect. But there seems to be not a lot of a strong signal. However, as we move towards the early 2000s, we see sea ice peaking. And I mentioned before, in 2014, we had this overall maximum in sea ice extent. This curve here shows the sea ice area. So the sea ice area peak occurred a few years earlier, but we see this slight upward trend. Then we see the loss of sea ice area and extent in 2015, a slight recovery to the end of that decade, and then this detrimental loss precipitated from 2022 onwards. So Hobbs and others worked on that, and they seek to study what the contribution of atmospheric drivers on this change was. And I hope you can read here. We have the different, basically, indices of atmospheric forcings. And overlaid over that, we see in black this curve of sea ice area changes. And this is a normalized curve to bring it all together, so it's standardized to 1 in the standard deviations. And you really can see that there is not a clear alignment between the two, between all these, the accumulation of the atmospheric indices and the change in the sea ice area. So the conclusion was that atmospheric drivers alone cannot in full explain the changes in the increased variance of sea ice. There have been numerous studies on this area, and I just wanted to share one with you that looks at trying to understand if there was regional congruence between atmospheric forcing and the sea ice change. And here in a study led by Ionita, we actually see that, for example, when we focus on the larger basins, such as in this case the Ross Sea, there seems to be a clear anti-symmetry between, in red, the monthly temperature anomaly taken over the Ross Sea area, with in blue the curve of the sea ice extent anomaly for this sector. So we need to pay attention more what's happening in those two deep basins, the Ross Sea and the Weddell Sea, to better understand the changes of Antarctic sea ice. We also have seen here a study recently published that tries to pull together the change of Antarctic sea ice with a number of other changes in the Antarctic Southern Ocean region. And again, we see this curve of Antarctic sea ice extent anomaly, and then compared to the actual edge anomaly, which is expressed in kilometers. And so it's the distance from the nearest southernmost continental edge. And there is a slight deviation in the signal. However, you very much see the regional distribution of those changes for both the curves. And we see that the 2023, the all-time so far satellite recorded minimum, exposed large amounts of the area north of the Ross Sea and that Wilkes region that we heard before, large amounts of the area to the west of the peninsula. Again, this bulge in to the north, and especially the northeast in the outflow of the Weddell Sea region, and a smaller ribbon all along the East Antarctic coast. So we have a lot of regionality in the signal, which is not surprising given the configuration. Okay, I better hurry up. So the changes, then we were looking in what is the contribution of the oceans. So there are very few measurements in the ocean. And so there is an array of current meters and other measurements in the Weddell Sea, shown in blue, and they indicated a change in the warming of the ocean waters by a change in the overturning circulation. This was even higher in the East Antarctic side. However, a moderation of the signal occurred right at a time where we went to observe the concurrent sea ice change in 2014. So there seems to be a clear signal that the accumulated heat in the Southern Ocean has risen to the top, and by doing so, it's preventing the formation of winter sea ice. I briefly covered that there is also an extended record. It's much shorter than what we saw in the cryosphere, and more work, to my belief, needs to be done. I know there are records that are going back a bit further, but we really need to work to have those records in both hemispheres to make better estimates. Just focus here on the very right panel, where we see those changes that the sea ice affects onto the radiative fluxes that has been evidenced in a recent paper that's cited here by Abrams et al. So the overall effect from the sea ice is really strongly going via the self-feeding effects of the albedo, so basically the change in the radiation balance. I'm skipping through this. I just want to give a shout out that sea ice is not just a system in the climate. It's also providing critical functions to to the ecosystems. It fosters diatoms and various other primary functions, and then it actually provides a feeding ground to the krill-centric food web. And the changes here are very difficult to measure and to quantify. However, we have a standardized data set that has given us an indication how these areas here, which are the main feeding grounds for the whole Southern Ocean, have shown increased vulnerability as the sea ice has declined in the area here, but also around the Far East Antarctic. This obviously then also affects higher trophic animals directly through the food chain, but indirectly through the food chain, but also directly through a loss of habitat, because they are really resting and having their nurseries on the fast ice, the small band of ice around the coast, which has shown a large collapse in the late 2010s, but especially in recent years, as we heard yesterday from Alex. There's a real crash, a halving in the amount of fast ice that survives. And with that, we see a decline in emperor penguin survival rates. So to come to an end, I just want to really call out, we have a need for much more focus on the sea ice within the global system. We need to embrace data methods, increase our uptake in new techniques, and we need to become much better and communicative in how we approach the modeling. We have seen some advances yesterday and on Sunday on different model simulations, and this is really promising. However, overall, we really are suffering from a loss or from a deficit of information. As you might have noticed that I barely talked about sea ice thickness, I mentioned the structure, and I briefly touched on the snow. But these are large unknowns with a lot of other sea ice variables where we really don't have detailed time series and not a good regional distribution. We lack consistent and sustained data, and I really encourage everyone who has involvement in Antarctica and think IPY to think not only in their discipline, but also to think others to support really cross-disciplinary data measurements across the spheres. And I also encourage us to become much more cognizant of what's possible, especially in the autonomous, but also with the upcoming remote sensing missions. So it's a call out for action for us scientists, and that's supporting what Chris said for the politicians. So thank you very much.
Well, thank you, Petra. And we have our last speaker now before we go to our panel session. And that is Professor Nick Golledge. Nick is an assistant scientist, primarily researching the Antarctic ice sheet using numerical models and field data. He's been a Rutherford Discovery Fellow, a lead author on the 6th Assessment Report of the IPCC, and is a Fellow of the Royal Society of New Zealand. Welcome to the stage, Nick.
Tēnā koutou, ko Nick Golledge taku ingoa. Nā mai haere mai atamare. So we've heard a lot about different domains of the cryosphere. And I'm going to talk a little bit about something a bit more sort of generic, I guess. We've heard a lot about sort of both gradual change and also the idea that there might be sort of abrupt changes lurking in the system. So this presentation hopefully is going to be around the latter, how we understand abrupt change. And a large part of what we're going to talk about is around regimes. Petra talked about the regime shift in sea ice. And so we sort of need to ask that question, like, what constitutes a regime? And how does that relate to things like climate surprises and abrupt change? So anyway, I thought I'd start with two sort of exemplars of the sort of change in the cryosphere, if you like. And you could choose many different indicators, metrics. But I thought we'd start with these two. So we've got Greenland melt area on the left-hand side and the Antarctic sea ice extent on the right. Now, when you look at these two, you can see lots of oscillations. These are systems that are behaving in a fairly oscillatory manner. But we do see abrupt change in both of these systems. The question is, why are they different? Are they different? So if we look at Greenland to start with, we can ignore the big sort of jump at around 1987. That's mainly a measurement issue. But as we go sort of forward in time from about 1987 onwards, you see a sort of upward trend. Okay, so the surface melt area is increasing gradually. Then there's a big spike around 2012, big melt area. This is, you probably remember it, this is the 1 year when pretty much the entire surface of the Greenland ice sheet experienced melt, which is quite phenomenal. And then it drops back down, and then there's a sort of a fairly elevated melt area, but the trend is kind of flat. So we see oscillatory behavior and a single abrupt event, an extreme event, if you like. If we look at the sea ice pattern, it's a little bit different. It's different in character. What we see here is the oscillations. This graph or forms of it have been shown many times in the last 24 hours, or 48 hours probably, and I'm sure we'll see it more over the next few days. But the thing that's interesting to me, at least, is that this abrupt change, 2015-16, is preceded by oscillations that are increasing in amplitude. And that's something that we don't really see in the melt area from Greenland. We see sort of oscillations with a fairly sort of constant amplitude, apart from that one big extreme event. So we've got sort of different signatures of abrupt change. Some are related to extreme events, others maybe are indicative of a system that is becoming destabilized, so we're seeing this increasing oscillation. The point is, we have different systems that behave in different ways, and quite often when we're trying to understand how those systems work, we can use numerical models, process-based models, or we can look at observational records. Now, the problem with observational records is that the present-day observations, recent observations, are relatively short. We've only got a few decades of data. Paleo records are great, but they tend to be sort of temporally uncertain in many cases and spatially sparse. So we tend to lean a lot on numerical models, and we put a lot of work into sort of including as many processes as possible into our numerical models. But the problem is that we tend to get results out that are a reflection of the processes that we put in. So there's a large amount of subjectivity in that approach. What we can do instead is use a dynamical systems approach. So we can think, instead of looking at processes and putting those into a model, we can look at models or use models that adopt a more holistic approach that try and simulate the behavior of a system in its entirety. And they're process agnostic in the sense that you're looking at just how a system, a generic system, evolves. This beautiful animation that you've been watching for the last few minutes while I've been talking would be showing one such system. So in the panel here on the right-hand side, you can see different states of this system. Now, this is the logistic map. It's a well-known dynamical system. It's basically the simplest possible model of a system you could get. It's got one equation. But we can use it to learn a lot about how generic systems behave, because this is a system that is, it doesn't depend on sort of deterministic inputs. It evolves primarily through internal feedbacks. Okay, so we have one parameter, R, which then allows the system to evolve. R basically controls the sort of volatility of the system, if you like. And then the rest of the evolution of the system depends on how X evolves through time, and then every iteration of X then informs the next value. And you can see on the right there that under sort of low values of R, you get these sort of monotonically stable solutions. And then it evolves into this sort of regime where you see lots of oscillations. But those oscillations are predictable, they're regular, they have a sort of fixed period. And then we go into a period doubling regime where we see lots of abrupt change, but it's still predictable. And it's oscillating within bounds. The amplitude is increasing. But then right down the bottom there, you'll see in the red, we have the upper end of this system where we have high values of R, we have lots of oscillations, abrupt changes that are now not predictable. And so that's the thing that we're interested in when we think about these sort of current cryospheric systems is, are there abrupt changes happening that are unpredictable? You can see this system evolving. And so depending on where you are in this system, you will get very different behaviors. That's the point that I want to make. So when it comes to understanding abrupt change, we need to sort of understand the regime of the system that we're looking at. And that's probably a little bit abstract, but we can look at sort of a more tangible example. So we're looking at a simplified geometry ice sheet model here, and we're applying a simplified forcing to that model. And I like simplifying things because it means that if you get kind of complex outputs, then it makes it easier to understand how they've arisen. So the simplified geometry it's just a circular ice sheet. The simplified forcing is hopefully what you can see here. This gray line that's oscillating. It's oscillating with a period of about 100,000 years, and it has a linear ramp, so that this is basically driving atmospheric and ocean warming, and it's increasing by 8 degrees over 1 million years. We're talking long time frames here. But what happens in the ice sheet is shown in the blue and grey shading. So we're seeing different mass loss components, calving, subshelf melt, surface melt. And you can see that there's different responses. In the first part of the run, you see that there's a very anti-phase response. The mass loss is peaking out of phase with the forcing. Towards the end of the run, it's very much in phase. Now we can use this data to say something about the different regimes that the ice sheet goes through. And if you look at the middle panel there, you can see that at the beginning of the simulation, there's a very blocky structure. It doesn't matter whether you're in a glacial or an interglacial state, the mass loss components are pretty much the same. So all I've done here is I've taken the data from panel A and then I've normalized it so that it's showing you proportions of the total. And then, of course, it changes through the rest of the run. And then we can analyze those sort of three components collectively by using the Shannon entropy. Now, Shannon entropy is very useful. It gives us a nonlinear measure of probability. So it tells us about the predictability of the system. So we can calculate the Shannon entropy for that window, that million-year simulation. And that's what's shown in the brown line. It doesn't reveal a great deal when we look at it in the time domain. But if you take the same data, shuffle it around, and then put it in temperature space, we can now see something that hopefully looks quite interesting. Hopefully what you can see here is that there's an abrupt jump here. We go from a low entropy regime into a much higher entropy regime, and then a sort of stepwise drop into lower entropy state. So we're going from basically a highly predictable system into a much less predictable system, and then back to a more predictable system under the higher temperatures. And the thing that I want to impress again is just how abrupt some of these changes are. So the system can go through abrupt changes if we look at it in the right way. So we can abstract from those data different ways of looking at it. We've already looked at the sort of phasing. So in panel B, you can see that shift in phasing from antiphase to in-phase. In the middle, we go through this sort of intermediate regime where things are very highly variable. The entropy is shown in brown, just a clearer measure. In D, we're looking at the variance of the entropy. So in a way, we're kind of looking at this sort of this intermediate regime, which is highly unpredictable, but even the unpredictability is unpredictable. It's oscillatory. But the thing that's most interesting to me about this is panel A, which is showing mass loss. Now, we tend to use mass loss as a kind of important metric for ice sheets because it tells us how much is going into the ocean, rising sea level. But it doesn't necessarily tell us much about the regime that the ice sheet is in. So what's happening here is we've got these three different regimes with quite clear boundaries, and yet the mass loss is just kind of changing. There's a period of sort of gradual mass loss and then gradual mass gain, but the inflection is somewhere in that middle regime, in the intermediate regime. So mass loss isn't the best metric, I don't think, for understanding whether the ice sheet or any other system really is stable or unstable. So we can take the simplified geometry models and we can look at something other than mass loss. And one of the better metrics, I think, is looking at surface velocities. Now, we're not just going to focus on sort of the fastest flowing outlet glaciers, Pine Island, Thwaites, Totten, whatever, Jakobshavn. But what about looking holistically? What about looking at the velocity distribution across an entire catchment or an entire ice sheet? So what we're doing here, we've got lots of different simplified geometry experiments in the map panels, and then each map panel has a scatter XY plot in log-log space where we're just looking at the sort of size-frequency distribution, if you like. And you can see that each different simulation which has different sort of flow parameters. So some are sliding more, some are carving more, some are deforming more internally, some have got isostatic rebound. They all have a distinct statistical signature in this sort of log-log space, and they trace out different patterns. So the different flow parameters give you a different signature, but they're also evolving through time. Under constant conditions, you can see how those points sort of jump around. The system evolves through time. So by looking at the system in this way, we can look at sort of structural regimes. We can also look at temporal regimes. And hopefully you'll see that on the right-hand side, there's a couple of examples of very nice sort of power law distributions, nice straight lines in log-log space. And we'll see a bit more of that in a moment. If we look at real data, so this is the measures data from Antarctica, the map panel shows all the velocity data across the continent. The log-log scatter plot shows just the grounded ice velocity distribution. But hopefully what you can see here is that there's some inflection. There's a structure in this data. We've got two different power law relationships, sort of separated by an inflection at around 300 meters a year, which corresponds to the gold line on the map. So the power laws here have got different exponents telling you that there's a different regime operating below 300 meters a year and a different one above 300 meters a year. And there's about 2 million data points here. So it's, I think it's fairly robust. So what's causing that inflection? I've given you two options so far. One could be structural regime differences. The other could be a change in velocity, so a perturbation to the system. And in sort of the ecological field, we look at sort of power law distributions and inflections in those as indicative of restructuring within an ecosystem. So maybe that's happening in the ice sheets. To explore that, I wanted to show just some data from a Greenland simulation where we impose an RCP 8.5 climate forcing. So the forcing is driving a big change in the ice sheet, and we can look at the response. And what you see here is that where that blue cross is, we see an inflection in the power law distribution. And then something kind of progressively increases over a century and a bit. And if we just zoom in on that part of the distribution, you can see that there's a couple of different things happening. One is that the data are moving upwards. The other is that they're moving to the right. So we're seeing more points in the system that are flowing at higher velocities. But the interesting thing is that when we look at the animation, the slope of those exponents actually remains pretty constant. So what's happening is there's a translation. Part of the system is now behaving in a different way. It's moving sideways into a higher velocity regime. So when we think about that Antarctic data, I would say that data is reflecting a structural difference, different flow regimes, whereas this Greenland data is reflecting regimes of different flow conditions caused by a perturbation. And I would just leave you with a few take-home points. And really, the bottom line is that when we talk about abrupt change and regimes, we sort of need to know what part of the system we're in, because the system is not going to change abruptly unless it's in a regime that allows it to change abruptly. If it's in a regime that's monotonically stable, we're unlikely to see sort of unforced abrupt change. And that's important, because it's those unforced changes that are the unpredictable ones. They're the ones that take us by surprise. Thank you.
I welcome our speakers to the stage now. I wanted to go first of all to Chris. Chris, so some of the flavour of your presentation was that things are happening faster than we might have thought or might have been projected. What do you think is the minimum sea level contribution for 2100 and 2200?
That's a very good question. And I would probably default to the IPCC report on that rather than my individual. I think if you look at that, then kind of we're almost guaranteed about half a metre. I would say that a metre is probably plausible by the end of century. If some of the trends continue, if as some people have hypothesized, that marine ice sheet instability has already just begun in somewhere like West Antarctica, or the Greenland ice sheet is close to a critical surface melt elevation feedback, then a metre would not be out of the question, possibly a little bit higher. I should add as well, by the way, that I really hope I'm wrong. I know it was a very depressing talk. It was something that, it was a paper that I felt we needed to write. We needed to kind of motivate some more research in this area in terms of what is a safe limit for the ice sheets. But I'm very happy to be proved wrong in the next 20 years if things start to, there's been a lot of snowfall in East Antarctica, that's helped mitigate sea level rise from there, and, Greenland maybe is, it's not quite fallen off the cliff, but we'll see. I don't know if Nick wants to come in on that as well.
You want me to give a guesstimate of sea level rise?
Well, Nick, what I'd actually like to hear from you is I think a lot of the projections, are, if you run them through, they arrive at a similar point, and perhaps in terms of sea level rise, the rate of change is perhaps much more debated. That's hugely policy relevant. What are the things as a modeller you think should be of absolute priority to resolve as quickly as possible? Whether that's field data, what is going to make a material difference to resolving the question of the rate of change that we're going to face?
Yeah, that's a good question. We are dealing with a largely deterministic system with some dynamical feedbacks involved. So I would say the thing that we need to know most is about the drivers of change. So it's going to be ocean forcing. Clearly, we need more observations. Anything on the surface we can observe pretty well, but anything under the ice shelves we can't. So that's clearly going to be one of the most important things that we need to understand. But I'm just going to fly the flag for dynamical systems and say that we also need to understand how systems change when they are unforced, because if you can force a system into a state where those internal feedbacks start to dominate over the external forcing, that's when you get unpredictable behavior. Okay, and at the moment, I think we're seeing largely deterministic change. In the future, we may see unforced change, and so that's something that we could probably well do with understanding.
Yeah, great. And I think there's a segue there to Petra. So Petra, and Nick showed early on the sort of like the increasing interannual variability in the sea ice, just as a sort of segue into his presentation. We've obviously seen a lot of variability or change in the Antarctic sea ice. Do we know enough about the Antarctic sea ice interannual and decadal variability to be confident about what's going to happen next? Could it recover? More than recover?
No, we don't know enough. I try to express that. So the regional variability for the Antarctic is so enormous, and there are processes at play that we haven't paid homage to sufficiently yet in some of the regions. But also, we don't even at a larger scale. Circum Arctic have a very clear understanding what the specifics driving the years-to-year variability really are. So I shouted out quite a few of studies, but I think we really need to have a much better observational understanding, and I also call out a third dimension. That's not only for the sea ice itself, but also for the ocean layers underneath. We could do with a lot of more information in there. So.
Yeah, great. And Lauren, I'll come to you, and then I'll come to some of the questions. So, Lauren, some of the presentations I saw yesterday, and perhaps some of your work today, seem to suggest that there's quite a lot of agreement now in the global projections of the future of the small glaciers. I came away from that sort of thinking, the first order problem's sort of solved. Your presentation sort of shone the light that actually there seems to be still quite a lot of variability at the local scale in terms of different methodologies. Have we solved the first order problem in terms of the future of the glaciers, or what are the critical things we need to advance?
Yes. Can you hear me? Yes. So I'll start by saying that I don't do any future projecting of glacier change. So that's all work that other groups have done that I wanted to highlight as part of this crisis in the cryosphere. Like you said, it does. People will use different models. The glacier MIP work has made big advances in this space. So I think, from my point of view, it seems like they're making great strides and can kind of maybe keep making these small improvements. Whereas when I think about it, maybe the big next steps are thinking more about the impacts of those changes. So doing more work around the water resources side of things, maybe hazards, that kind of stuff.
Great, thank you. So I've got a question here from Yu Chung Lin for Chris, and maybe others want to dive into this. So could you talk a little bit more about the Antarctic ice sheet tipping points? Is there any consensus on what is the consequence of tipping points?
Yeah, that's a great question. I think I'd first point out that I think there are pros and cons of just kind of the tipping point approach actually in ice sheet research. You know, we don't know exactly where they are. It's been pointed out that they can be a bit of a distraction. You know, if we're wrong, if we say there's a tipping point at 1.5 for, say, West Antarctica, and then we hit 1.7 and nothing's happened, that's a very easy excuse for policymakers to ignore the science and say, well, you guys clearly don't know what you're talking about. So I think we have to be careful sometimes about tipping points with ice sheets. I'd also point out that for somewhere like East Antarctica, to kind of simplify it to one temperature threshold is a bit naive and probably a bit silly in the sense that, you know, we've got at least 3 large marine basins. My own feeling would be that each of those basins probably has a different tipping point, and that there are large uncertainties on all of these tipping points. But if there is something in the system that leads, as Nick alluded to, that leads to a kind of almost like a regime shift, that leads to a change that essentially becomes disentangled from the external forcing, like marine ice sheet instability, then, you know, that we know from the paleo record that can lead to very rapid jumps in sea level, that those processes seem to be, or that process seems to be theoretically robust, and you could see you know, several meters, let's say, of sea level rise within just a few centuries. And we've seen that in Meltwater Pulse 1A 14,500 years or so ago. The source of that is debated, but we know it must have come from the ice sheets, and it must have come very rapidly from the ice sheets. So that we just know that there are kind of processes out there, and, you know, it's likely that they are triggered by certain temperature thresholds at certain points. But
yeah, I'm happy to talk about this because, yeah, I think with tipping points, it's a big distraction. I think we can think of the ice sheets as a tipping element within a complex system, but I think the whole idea that there's a tipping point is erroneous, largely because ice sheets don't respond to a certain temperature, they respond to the integrated forcing. So really, it doesn't matter if we hit, 3 degrees. There's no magical tipping point there. What happens to the ice sheet is a consequence of how long we are at a certain temperature. Okay, and there's lots of interannual variability, interdecadal variability. So the integration of that and how long it persists is what is important for the ice sheet. The longer we are warmer, the more we're going to lose the ice. It's fairly simple in that respect. In terms of, using the past as a analog for the future, it's tricky. Chris has mentioned Meltwater Pulse 1A, but the Antarctic ice sheet was in a very, very different configuration during Meltwater Pulse 1A. It had large areas of grounded ice in the current marine embayments, which were very close to flotation. So a small change in thermal forcing or sea level just destabilized a large amount of formerly grounded ice and made it go afloat. So we lost lots and lots of ice very quickly. So that clearly was maybe some sort of threshold. But we don't really have that configuration anymore. We have a very different configuration. We do have a lot of marine-based ice, but the ice that's sitting above those marine basins is very thick. It is not low-profile ice like we had at the LGM. It is not a low aspect ratio ice sheet. So the configuration is different. You could say it's a different regime.
Great. So Petra, I'm going to come to you. So this is from Dave Sutherland. So you didn't mention ice sheet change as a driver for Antarctic sea ice change, I guess. Do we know how meltwater input or changes to ice shelf area and iceberg extent change sea ice area?
We probably have some examples with measurements and where we have an idea, but I would say the biggest information at that area really comes from the models, and I suggest that the models have incomplete knowledge. So I know there were some studies when we saw the increasing sea ice leading up to 2014 maximum, but some of them, have shown that they might play part of it. The freshwater parts, the lenses, keeping the warmer water away. They haven't really come back. And the big thing is really also the different time scales. When Nick talked, I saw a big lambda in my inner eye, and I thought, all the responses have a different time decay scale. So on the glacial side, it's so much slower. On the ice shelf, it's a different one. The glaciers, a different one. And then there's this thin sea ice sitting there, being like running with a very high heartbeat. And when they, depending how they become triggered, that's really, I mean, the question alludes to it, you have something changing on a larger, slower timeline to the sea ice on the faster one. We don't have Antarctic the knowledge to say. Okay.
I'm going to come across to measurements now. So Jim Salinger has asked about Lauren about would the errors from the New Zealand glaciers decrease with more measurements? And he says with more science funding. Agree. No controversy there. Compared to the European Alps, where you can literally make measurements daily off a gondola or something like that. What would the material? How many more measurements would you need to make, or where would you need to make them to make a really major difference to your mass balance estimates?
Yeah, I think Europe just seems so different compared to things here. Like they have so many measurements that have been going on for over 100 years, which is just such a different scale. So I think both some more, but also looking at some of the big glaciers that are kind of most important for water storage, and have seen some of the big changes, like the map that I showed in one of those first slides of that Aoraki region. That's where maybe a third to half of the ice in New Zealand is in that small region. Whereas the photo survey and the mass balance measurements, my theory is that they were selected because they were kind of smaller and more kind of feasible to make measurements at, and they've only just gotten smaller over the 20 to 40 years that those have been happening. So, yeah.
Cool, thank you. So, and I wanted to come to you, Chris, to think about early warnings of change. And, I think there's been a bit of thinking in the Arctic and Greenland around them. I think BAS has perhaps got a program around this. What would an early warning system in Antarctica look like? We've got satellite observations. But what are the critical early warning measurements of change that we don't have?
Well, I actually think that we do have most of the measurements we need, and I could envisage in the next 5 or 10 years with deep learning and that you could have a system set up which pulls down, the altimetry data, which is looking for surface thinning in marginal areas, and perhaps looking for signals that propagate inland. If that then is coupled with, say, grounding line retreat, which you can get from things like SAR interferometry, you've got the measures velocity data that's being pulled down every week or so. So I think it's within our capabilities within the next few years actually to be kind of automating these processes where you could look for those signals of what we might describe as dynamic change. So thinning, grounding line retreat, potentially acceleration of the surface flow speed as well. They'd be the things that, as somebody who uses remote sensing data, I would be looking for as an indication. But I think, in terms of projecting what that might look like, I think that's where the modelling comes in. And I think it's been mentioned already probably several times at this conference that conditions beneath the ice shelves and the subshelf melting will be absolutely critical to what happens in the future going forward, and those observations, are scarce compared to the kind of the remote sensing that we can get from airborne and satellite data.
I imagine, Petra, you might have some thoughts from the ocean, fast ice, sea ice perspective.
We need to have many more well thought through surface and in situ measurements. We're really lagging the detailed understanding of those when we bring more and more components in. I very briefly touched on the ecosystem biological feedback onto the sea ice, and there are some limitations. You know, the photosynthetic activity is limited, you know, by the sun incident angle and so on, while the sea ice is exposed to the underlying ocean and the atmosphere obviously all year round. And so you have these, you know, kind of if-then cases built in, and I know that we don't have sufficient measurements. I mean, if we go and send people on the ice, we miss out the early freeze-up, we miss out the late break-off, and there are critical periods, especially that freeze-up where we now see increasingly the fast ice growing. It would be sufficient to deploy some autonomous instrument on, but then, you know, we don't quite get there and we lose all those measurements. So I think we lose at least 5 months a year for the in-situ measurements, and I definitely believe that they are critical. I mentioned autonomous instrumentation, so you could deploy something if you had, you know, a heavy lift drone or so, but it should be achievable if we had a will and if we had the resources.
Yeah, well, and that maybe segues into Manako McLeod's question around have we got the balance right between, and I don't really necessarily like the idea of playing off the Arctic versus the Antarctic, but nonetheless, the infinite resources. Have we focused enough on the Antarctic versus the Arctic? I mean, Chris, you've talked on West Antarctica versus East Antarctica. Have we got the balance right in terms of the regions of focus and especially where the risk sits? Either of you two at the end. Chris?
Well, I switched the microphone on. It's actually a question. Having, you know, spent a lot of my professional life down in the southern hemisphere and looking at the Antarctic region, and now in the UK, I realized that, you know, there is I mean, just external drivers, the funding, the drivers, the interest at the moment, and I think in the last, 5 or 10 years, more than ever, the political drivers, the social drivers are sitting much more in the Arctic, because that's where, I guess, a lot of the science funding sits, where lots of the cognizant population sit. So we really talk a bit, this debate also needs to include, you know, the Global South discussion, I think, very much. On a physical scale, I think both are still understudied, and I think, you know, different areas are better studied. I mean, I can't remember, Thwaites was mentioned and so on. Where there are dedicated campaigns, you know, parts of Greenland are obviously very well studied, but there is so much terra incognita that it's really not funny.
No one else wants to bite on that one. Okay. So one from Rob Massam for Nick. So the disintegration of the Larsen B in 2002 was shocking in its abruptness, you know, within, you know, 8-fold ice discharge and the glaciers feeding into it. What are your thoughts on ice shelf vulnerability?
Big question. Yeah, Larsen B was a good one. It was abrupt, for sure. But the question is it abrupt in the sense that maybe we see that abrupt change in the sea ice, or is it abrupt in the sense that we saw that extreme event in Greenland? I would argue it's the latter, because when you look at the ice sheet response to that ice shelf collapse, it was transient, right? We saw the glaciers speed up straight after the ice shelf collapsed, but then they slowed down again. So in terms of the sort of the integrated response, it was relatively modest. So thinking more about the larger ice shelves, I'm going to be a little bit controversial and say maybe it's unlikely we will see large-scale instantaneous collapse of the major ice shelves. I think they're too extensive and too thick at present. I think we're more likely to see sort of localized collapse of certain sectors as they thin. I think there'll be a certain amount of strain partitioning during that collapse process, so that you will see sort of fragmentation in certain areas that doesn't propagate across the whole ice shelf. In terms of the sort of the drivers, we heard a bit yesterday, I think from Phil Reed, about coastal exposure. Clearly, the more these ice shelves are exposed to long period swell and ocean warming, probably even wind forcing, all sorts of things, the more likely they are going to be predisposed to collapse. So again, kind of coming back to that sort of dynamical systems lens, we can start looking at that propensity to an abrupt change and think about like the combined impact of all these external forcings that cumulatively lead the system towards a regime where they are then vulnerable to a sort of wild card response.
And while you've got the microphone, Nick, there's a question here from Marwan Katurji. So do you think the Antarctic dynamical systems regime shifts can be governed by dimensionless parameters reflecting different forcings analog to atmospheric turbulent systems?
Yeah, so I guess the heart of this question comes down to whether we can use these sort of abstracted dynamical systems approaches to understand real-world behavior. I would say we can, by analogy. You know, you think of, say, one of the most famous dynamical systems, like the Lorentz attractor that was essentially devised to understand atmospheric turbulence, right? So there was a grounding in a physical system there. But the point about these models is not to put it in sort of rigid process space or parameter space. It's about understanding system behavior and sensitivity of those systems. And I think we can explore a lot of complex systems by using simple models, and we can learn lots of things about those systems. The job then becomes how do we then take the findings from those simple models and compare them to the observations and see, well, actually, yes, this one is behaving like that, or no, that one isn't behaving like that. That's when we have to do the sort of critical work, and maybe there's something we can learn. But again, we need the observational data to do that validation.
Thanks, Nick. So, Chris, can I come to you? Look, this could be a Dorothy Dixer in terms of East Antarctica. I'm trying to ask it in a way that isn't just, should we do more work at East Antarctica? But that's the question I'm going to ask effectively. But I mean, you know, East Antarctica is massive. Where do you know, if you had, you know, a season of icebreaker time and a bunch of twin otters, where would, you know, and, you know, well, you're sort of partly a field scientist, aren't you? But where would you have the scientific community focus, given the changes you're observing, at least at the fronts?
I think you've done a huge disservice to field scientists describing me as one. I think the three marine basins are obviously candidates for needing to know a lot more, and I find it really interesting that there's kind of mixed messages between observations and models. You know, I think, you know, Nick's done some work that suggests that the recovery might be very vulnerable, and I know there's some other modelling might be published soon that suggests similar. And then, you know, we've got the Wilkes Basin and the Aurora Basin as well. And actually, most of the change seems to be over the Aurora Basin, so, you know, in Wilkes Land. I know that's confusing. But actually, I think some of the work that was done on you know, this notion of this kind of thin ice plug around Cook Glacier and Ninnis and places like that's one area I think I'd be focusing on. But it's kind of like, you know, it's difficult because, you know, as soon as you do need these campaigns. You know, I think the Thwaites project and some of the work that's been done in the OSC is a really good idea. When nations collaborate and you throw a lot of money at it, you really can understand these systems, but it's you know, it's relatively easier to get there than some of the areas in East Antarctica, which is the problem. But probably the Aurora Basin and the Wilkes subglacial basin would be my kind of prime candidates to go and look at next. I think we're potentially on the cusp of something happening there in the next few decades. Time will tell.
Petra's nodding along. Did you want to add anything, Petra? You don't have to, but did you have anything in particular to add?
Yeah, I think it would be a beautiful location to have, you know, transect going from the near coastal, like from the terrestrial shelf into the wider ocean, exactly at that longitude range. We typically don't have any much sea ice information there. I think coastal ocean it's not measured well in that area, so it would be a beautiful site, pretty virgin, and from the marine side, and I guess it would really be, you know, an analog to, I guess, weights on, I don't want to say steroids, but, you know, more complete picture in that area.
Great. So I think we're going to pretty much draw to a close. There's a question here that I think would be good to dwell on as we finish from Pasang Sherpa. So how are the panellists considering crisis as cryosphere communities continue to live with one crisis after another? And I guess that goes to the heart of, you know, one person's crisis is another person's just emergency. And you know, and above the average of global climate models, which are, you know, smoothing out a lot of the variability in that sense. I don't know if Lauren, you wanted to have a crack at that one? Yeah.
Yeah, that feels especially maybe relevant to mountain glaciers or closer to humanity. There are so many communities that are already being impacted. In Peru, there's a community. The glacier has retreated so much that there's now a lake at the end of it. They're at risk of these glacial lake outburst floods and are trying to sue a German energy company to get some funding for monitoring that risk to be prepared for it. All the communities in Asia that have been impacted by the glacial lake outburst floods. I don't know if I have an answer or even exactly remember the comment, but yeah, just thinking about how these changes do really impact people in their lives, and yeah, maybe a good thing to continue to think about for the next few days and wrap up as we finish or bring together our final thoughts on that last day of if there's anything more we should be doing, or yeah.
Petra wants to say something.
Sorry.
Yeah, and then we'll finish.
If I may indulge, I think the biggest crisis is, in simple words, that the science is something that's seen as discretionary and the science information is not communicated and acted on. And so I think it's speaking for every science that we can think of, that, you know, there are other more urgent priorities in people's minds, in decision makers' minds. And I guess to a degree it's how and what we communicate and how we choose to do that. But I also believe, you know, we really need to level it up and, you know, engage more and make science more engaging.
Yeah, great, thank you. Could you all join me with thanking the panellists one more time?